Welcome back, students. In this lecture, we will learn the applications of Stokes theorem because proof is not in the engineering courses, so I am not including the proof in this lecture. But if anyone of my student or otherwise need the proof, you can put in the comment and I will upload a separate lecture for that. So let us learn what is the theorem and what are the applications, because this is a very important theorem. So let us first take the statement and understand what it says. So the Stokes theorem states that if a vector valued function v and its first order partial derivatives are continuous on a surface S, and if a closed curve C is bounding the surface S, then the line integral of the vector v on C is just directly equal to the surface integral of curl of v over the entire surface S. Here the vector ds is just n ds, so as n at the unit normal, outward drawn unit normal, and you already know this. We have mentioned these things in the earlier lectures. And the boundary that bounding the curve S, the boundary that bounds the surface S is most often referred to as bounding curve. Means most frequently we will term it as bounding curve, not the closed curve. You can see there is a figure. This is a cone and the cone is cut by a slant surface. So the surface of cone is marked in purple color, and it some in red color there are some unit normals at different points. So each point has a separate unit normal in a particular direction. There is another figure. This is a cylinder, and the cylinder is cut by xy plane and a slant plane y plus z is equal to 2. The surface of cylinder is in gray, and that by a plane y plus z is equal to 2 is marked in as blue. There is a sphere. The sphere is cut by some plane parallel to xy axis, and the bounding curve is shown in yellow color. The unit normals at spherical surface are shown in red color, and each point has its own unit normal. So there is a cone, again a cone. This cone is also cut by a parallel plane parallel to x-axis. So this surface of the cone is shown in white, and the plane that cuts the cone is shown in blue color. And what are the application of this? The application is very easy because line integral and surface integral are equal. So whenever which of the two is easier, we will have the option to calculate the one for the other. So this is the application. And there is a very necessary thing that you must remember, that I have saying it a little imprecisely, means that is not exactly the definition, but it will help you remember the things. The bounding curve is always for an open surface. For example, you can see there a sphere. Sphere is cut, so this is open. So it has a bounding curve. This cylinder is cut, therefore it is open. The cylinder surface of the cylinder is open. The blue surface is of a plane, so cylinder is open. So it has a open surface, and therefore it has a bounding curve. This you can see the cone. Cone has a purple color surface, and it is not closed. It is open. So it has a bounding curve shown in red. Means red color curve shown in the cone is bounding the surface of cone. So always open surfaces have a bounding curve. Closed surfaces do not have a bounding curve. So in this sense, some authors say that closed surfaces also have bounding curve. So we can assume that if a closed surface has a bounding curve, you can think that two open surfaces are composed to form a closed surface. For an example, take this sphere. You can see the sphere is closed. This is complete sphere. So I say that it has no bounding curve, or in other words, you can see that I have colored the sphere in two different colors, one half in purple color and second half in blue color. So you can say this closed sphere is composed of two open semi hemispheres, purple hemisphere and blue hemisphere. So each hemispheres have a bounding curve, but the bounding curve of the purple hemisphere will be oriented in just opposite direction to the bounding curve of blue hemisphere. However, both the bounding curve is same. So this is how we understand for the closed curve, but you will never actually you will never need a closed curve. Questions will be always for the open surfaces. So for open surfaces you will find the bounding curve easily if you remember this note being a little imprecise. But even if it is imprecise, I have corrected the definition, so finally it is precise and correct. So let us take another statement that enables us to use the Stokes theorem more accurately and more easily. So it states that if vector v satisfy the conditions of Stokes theorem, and there are two open surfaces, one is S and second is S dash. If both these surfaces are oriented in same direction and both have same bounding curve, then the surface integral of curl V on both the surfaces are same. So this is very good theorem, and this will enable us to use Stokes theorem more easily. So let us see how will it enable us to use more easily. So first, this is a notation of unit outward drawn unit normal. I will come to this point later. So suppose this cone, you have to evaluate a vector on the purple surface. So this theorem says that you should mark that bounding curve is marked in red. So the bounding curve in red color bounds both the surfaces, the purple and the green. Purple surface is the lateral surface of cone, while the green surface is part of some plane that cuts this cone. So the bounding curve in red color bounds both these surfaces, the purple and the green, but it is hard to integrate a vector on the purple surface. But this theorem enables us to integrate the same thing on the green surface. So it is easy to find the unit normal on the green surface, and it is easy to evaluate an integral on the green surface because it is plane. Similarly, this cylinder, it is a little difficult to not much, this depends question to question, but for a question it may be difficult to integrate on the gray surface, but that will be easier to integrate on the blue surface because that is a part of plane, and bounding surface is marked in dark blue, and that is same for both. Similarly, this cone, the cone has lateral surface yellow and a plane that parallel to xy plane, there is a plane parallel to xy plane that cuts this cone, and that marked in blue. So it is easier to find the normal on the blue surface, and instead of integrating some function on this yellow surface, we will integrate on the blue surface. Similarly, this is a sphere. So instead of evaluating the integral on the spherical part, we will just evaluate on the plane. Plane is marked in yellow color. So we will need the unit normal on the plane. So now come to the note I have written. If you have to integrate a line integral, if you have to evaluate a line integral, means you have to integrate a vector along a closed curve, then it will be line integral. So Stokes theorem says that you can integrate the uh, vector curl of the vector on the surface bounded by the closed curve. So just see the sphere. Just see the sphere. The red circle means the greater circle of the hemisphere bounds the hemisphere because the sphere is open. So one way that some line integral on this red circle can be integrated as a curl of the function can be integrated on the hemisphere surface, and this theorem enables that the line integral of a function on the uh, closing circle means this bounding circle means the red circle, that is equivalent that we integrate the curl on the yellow plane means yellow surface, so it is easier to evaluate on the yellow plane. So this is and more precisely you will get these things when we will take questions. So let us start with some question. So let us take this first question. It says using Stokes theorem, find the line integral of this vector v along the circle. So what is the line integral? We already know, we have studied in the lecture of line integral that line integral of this vector v is written as c v dot dr, and v is given, dr you know, dr is dxi plus dyj plus dzk. So I am writing here because this is the first question. So dr is equal to dxi plus dyj plus dzk. This is dr. So take the dot product of v dot dr, then we get the line integral c 2x minus y dx minus yz dy plus minus y square z dz. So one way to integrate this is along the curve and integrate these three parts separately, but this seems a little hectic, so let us use the theorem, and I am erasing this part again. So let us use the theorem. By the use of this theorem, what the theorem says that this is equivalent to a surface integral of curl of v over ds. Then now you should find what is the ds. So because this is a circle and this lies in xy plane, so simply this, the area, the region bounded by this circle is s, and bounding circle is circle itself. So just find the curve and then we will write the other thing. So just find the curl. So curl is what? Curl of v. So I hope you can find the curl very easily because we have already learned these things in previous lectures. This is our curl v, and what is this ds is actually ds vector. This is ds vector curl v dot ds. So what is ds? You already know that this is written as curl v dot n ds. Ds vector means unit normal to n and unit normal to the surface, and ds is scalar. So what is n? We have discussed that n is unit normal to the surface s. So because this is the surface s and this is xy, this lies in xy plane, so normal to entire xy plane is k cap. So the n to this surface will be cap, means n is k cap, n is k cap. So I am again repeating, k cap is normal to entire xy plane and this region lies in xy plane, therefore unit normal n cap is just k cap. So write these things here. So I is equal to what? I is now equal to this surface integral, and curl v is k, so this is k, then n is also k, so this is k, and ds is just dx dy on xy plane. This is the area integral. So k dot k is 1, so we have got just dx dy, and this is area integral. And what is this area? This is just area of the circle. So this is just area of x square plus y square is equal to 1. So this is area of this circle. So this is directly we can find without integrating. Area of unit circle is just pi. So this is our answer. The next question is, if V is a vector given by this x square y square I plus xy j plus xzk, then we have to find this line integral v dot dr, and the closed curve of line integral is the bounding curve of hemisphere given by this of radius a square and z greater than 0. So let us first draw this bounding this hemisphere. Suppose not looking very good, but my drawing may not be appealing, but just consider that this is the hemisphere, and that this is x-axis, this is y-axis, and this is z-axis. So I am also writing the unit directional vectors, standard unit vectors they. And now this sphere has equation x square plus y square plus z square is equal to a square, and this circle marked in red has equation x square plus y square is equal to a square. You can see that this circle bounds the two regions. One, the hemispherical surface region, and second, a plane bounded by the circle itself. So the theorem just after the Stokes theorem enables us that integral on the surface of a sphere will be equal to the integral on the surface bounded by the circle on xy plane. So let us solve the problem. Using Stokes theorem, means Stokes theorem enables us to write this integral v dot dr as surface integral of curl v dot and ds, and the alternate theorem enables us that we will take this ds as the part of xy plane bounded by the circle, this plane. So the outward run unit normal n will be unit normal on this plane, means xy plane. So let us find curl v, and we have done a lot of questions for curl v, so I hope you can find it easily, and this comes out to be minus zj plus yk, and n cap is as, and I have just mentioned that we will take this surface bounded by the circle on xy plane. So here n cap is our k, so n cap is k, and we take this n cap and take the dot product separately. So n cap is equal to k, and therefore k, this k, and therefore curl v dot n cap, this is just minus y, this is yk. So curl v dot n cap is just minus y. Now what is dx? So dx is obviously ds is dx dy. So ds is just dx dy, and now we can perform the integration. So our I becomes this surface integral, and curl v dot n is minus y, so you can write it minus y, then dx dy, and you can see that limits of dx dy means limit of the variable xy can be taken from this circle. So it is very easy, just write here s, and then we will take this in polar coordinates. So let us consider in polar coordinate, and for that we will get x is equal to r cos theta, y is equal to r sin theta, and dx dy is equal to r dr d theta. All will r radius vector will vary from 0 to a, theta will vary from 0 to pi. So 0 to 2 pi. So I becomes minus this double integral 0 to a, 0 to 2 pi, and y is r sin theta, then r dr d theta. You can finally write is 0 to a, 0 to 2 pi, and r square sin theta dr d theta. These can be integrated separately. R becomes r cube by 3, and limits are 0 to a. Sin theta becomes minus cos theta, and there is a minus already existing, so I am taking the combination, so minus gets cancelled with minus 1. So this is cos theta, and limits are 0 to 2 pi. So the integral is finally 0 because cos theta is same at 0 and 2 pi. So this is our integral. This is a similar question, but little different, and we will take it. Let this be the sphere. We have the question to evaluate this line integral, and we will use the Stokes theorem. So let this be a sphere, this be x-axis, this be z-axis, and this be y-axis. So it says that bounding curve is consisting of the intersection of two surfaces. One surface is the sphere, and second surface is plane x plus z is equal to 1. So obviously sphere has radius 1. So this point is 1 0 0, and this point is 0 0 1. Further, the plane x plus z is equal to 1. So just you can draw a line and consider the plane visible from the lateral side. So this is the plane, and equation of plane is x plus z is equal to 1. So what is the bounding circle? When the plane will cut this sphere, you will again see a circular part here. So this is the bounding circle that I have marked here in blue. So this is the bounding circle. So we need to and the C is given there. This is the intersection of this. So this is C. So the line integral is given along C, and we will evaluate the same using Stokes theorem, means surface integral. So let us start this. I is equal to, this is V dot dr, and this can be written as surface integral of del cross V dot n ds. And what is ds? Ds stands for the surface. So what is surface? Surface is this surface. This is the surface, means surface of intersection of the plane and the sphere, means surface bounded by this green circle. So this is the surface. So first we will need to find unit cap n, and del cross V means curl of V. So let us find anything first. Let us find del cross V first. So what is del cross V? Minus I plus J plus K. I am writing directly because I hope that you know how to find curl. So you will find this, and again this is a practice part for you. Then we will need to find this n cap. So I have already told you that we are considering this surface bounded by this green curve, means plane bounded by this green curve, green circle. So we will find the normal to this circular plane. So n is equal to this grade of x plus z is equal to 1 del x plus z minus 1 divided by magnitude of del x plus z minus 1. You know that we find unit normal in this way. This is gradient of the surface, and this is magnitude. So what this comes out to be, I plus j by root 2. So this is our unit normal. Now we will find curl v dot n. So del cross v, del cross v dot n. What is this? So I, this is del cross v. So I dot minus, first take minus, so this is 1 plus 1 by root 2. So this is just minus root 2. So we have obtained the curl v dot n. Now just put these values and integrate. So let us start. I is equal to minus double integral root 2 ds. And what is this? This is just minus root 2 times double integral ds. What is this? This is area of the circle. This is minus root 2 times area of the circle, means bounding circle. This is area of bounding circle, of the bounding circle. And for your uh, easier understanding, I am again drawing the same. So if this is the bounding curve, this is the sphere, this x axis, y axis, and z axis. So the x plus z is equal to one plane cuts the sphere in this way, and you will get a circle. This will be a circle. You can draw a fair diagram, fair graph, and you will see it more clearly. So this is the circular region bounded by this circle C. This is circle, means circle in green. So now we just need to find the area of this green circle. So this is O, and this is the distance. Let us mark this in other colors so that it become easier to you to grasp. So this, and this is also O to this line, this distance we need. This distance are simply we need the radius of this circle. What is the radius of the circle? So I am marking it in thick line. This is the radius. So how will we find this radius? So you know that this part, this represents the radius of the sphere. So this is 1, and again this line represents, let me mark it A and B, the cut by plane. So point on z axis is B and point on x axis is A. So this line means presentation of plane. This is also of length, one on x axis and one on z axis. That means OB is 1 and OA is 1. So what is AB? AB square is OA square plus OB square, and AB square, just this 1 plus 1 is equal to 2. So AB is just root 2. Then what is this radius? Radius is just half of AB. So let us name the radius as R. So R is what? R the radius of the green circle. This is just 1 by 2 root 2, means it is 1 by root 2. So now what is the area? Just complete the question by writing this. So minus 2, and area bounding the circle, this is pi r square, means 1 by root 2 square, means 1 by 2. So this, and that is finally pi by root 2. This is our evaluation to the given integral. And now let us take a little different problem. So this is the line integral that is already given. And what is the curve C? C is the boundary of a triangle given by these 3 points. So let us first draw. So this is z-axis, this is x-axis, and this is y-axis. So it says that the triangle has vertices and 2 0 0. So let this be 2 0 0, 2 0 0, then 0 3 0. So let this point be 0 3 0, and then 0 0 6 2 3 4 5 6. Let this point on z axis be 0 0 6. So just connect the points and we will get the triangle. So this triangle forms the curve C. So if we name the origin as O, this is A, this is B, this is C, then C is exactly AB plus BC plus CA taken in counterclockwise direction. So this is our triangle, this is C. Now we will evaluate the integral using Stokes theorem. So what Stokes theorem say? So first we need to find out the vector and vector separated from this. So x plus 2y dx plus x minus z dy plus y minus z dz. You know this can be written as x plus 2yi plus x minus z j x minus z j plus y minus z k dot dr. This dot dr is dxi plus dyj plus dzk. So let us take v as this vector as v. So we have the given integral I is equal to integral c v dot dr, and then by use of Stokes theorem we can write it as a surface integral of curl v dot and ds. Now what we need to find? First we need to find curl v. So v, we will find it, and then we need to find this n cap. What is n cap? Actually, consider this ABC triangle. So there is a slant plane bounded by this triangle, and the unit normal to that plane will be taken as n cap. So this is something of this type. So just unit normal will be obtained from the equation of this surface. So let us first calculate curl V, and this is again a homework to you, means a practice question to you, and this is 2i minus k, and I hope you will calculate it. Now we need to find n cap. So first write the equation for this plane bounded by the triangle ABC. So equation of plane bounded by ABC, or you can say the equation of the plane on which the triangle ABC lie. Equation of the plane on which ABC, the triangle ABC lie. On which the triangle ABC lie. What is the equation of this plane? This equation is x by 2 is equal to, or you can also say plus, so x by 2 plus y by 3 plus z by 6 is equal to 1. This is the equation of plane, and the triangle ABC lie on this plane. So we will find the unit normal on triangle ABC, means we will find the unit normal on this plane. So if this be denoted as phi, so first find n means grade phi, and what is this? This is 3i, no, sorry, this is not 3i, this is 1 by 2i, 1 by 2i plus 1 by 3j plus 1 by 6k. This is normal, and now divide by the magnitude of this, so it will be easier to take 1 by 6 common, and we can write 2i plus uh, sorry, not 2i, this is 3i. So this is 3i plus 2j plus k. This, when you take 6 common, the first I component becomes 3, j component become 2, and k is 1. 1 by 6 is common, so this is n, and then n cap is n by magnitude of n. So this you can write 1 by root 14 plus into 3i plus 2j plus k. So this is our unit normal. Now put the things together, means curl v dot n. So curl v dot n, curl v dot n. So we will calculate. So you know that curl v is given by 2i minus k, and then dot n cap means this unit vector, so we will get 1 by root 14 and take the dot product, so 3 into 2 for I components, this is 6, and my j component is 0 in curl v, so this component becomes 0 in dot product, and minus k into k dot k, so this minus 1, so we just get 5 by root 14, means curl v dot n is 5 by root 14, a scalar quantity, and not only scalar quantity was also constant. So because curl of v dot n, this become 5 by root 14, and we have I is equal to this surface integral curl v dot n ds. So we just get surface integral or the region bounded on xy plane by the triangle, this 5 by root 14 dx dy. And for the sake of completion, or simply you can say for your easiness, I am again marking the triangle. So this and this O, A, B, C, this as 2 comma 0 comma 0, this point B on z-axis 0 comma 0 comma 6, and this point C on y-axis 0 comma 3 comma 0. So let us draw this separately on xy plane. Why I am drawing? Because we have considered ds as projected surface on xy plane. We have written ds as dx dy by, sorry, this is dx dy by n dot k. We have already discussed a lot about this. There's projection of this plane ABC on xy plane will be triangle marked by OAC, this, this, and this is positive direction. Now we have also discussed that ds can be written as dx dy by n dot k, so you can learn a lot about this in the previous lecture of surface integral. So we just get as 5 by root 14, 5 by root 14, 5 by root 14, and the double integral dx dy by n dot k. What we need, we need to find n dot k. So because we have n and we have k, so n dot k is exactly 1 by root 14, and put this n dot k here, so 1 by root 14 will cancel 1 by root 14, so we just get this dx dy over the region r. What is the region r? This is the region r, marked by this triangle x-axis, y-axis, and you know x-axis has intercept at 2 and y has intercept as 3. This is origin. So what is this dx dy? This is just 5 times area of triangle. Which triangle? OAC. O on origin, A on x-axis, and C on y-axis. So OAC. And you even do not need to integrate this because you know the area of this triangle.
So this is 5 into just half of base into height. So base is 2 and height is 3. So you get 15 units. So this is the area, and we obtained using Stokes theorem. We can also take some questions on verification of Stokes theorem. And what does it mean? Means find an integral using Stokes theorem and without using Stokes theorem. That is called the verification. Means you verify by direct integration that the same result comes from the Stokes theorem. So if you need, you can comment in comment box and I will upload a separate lecture. Otherwise, that is very easier. And in next lecture, we will learn the Gauss divergence theorem. This theorem deals with the equivalence of integral over a surface area, closed surface area, and the volume bounded by the closed surface area. So just keep waiting and must watch this lecture.